Faraday's law states that the induced voltage in any closed circuit is equal to the time rate of change of the magnetic flux linkage by the circuit. Lenz's law dictates this induced voltage to oppose the direction of the flux inducing it. This can be broken down further by defining the flux linkage as the number of turns in the circuit times the flux through each turn. Assuming that the number of turns in the circuit remains constant, the differential can be applied to the magnetic flux term. This concept typically manifests itself in three ways. The following expressions assume the number of turns is equal to 1. Transformer EMF is the case where the magnetic field varies with time, while the circuit remains stationary. Motional EMF is the case where the circuit is moving with respect to a static magnetic field. And the combination of these ideas is the case where a moving circuit is exposed to a magnetic field that is also changing with time. This demo will take advantage of the first case, transformer EMF. To do this, a time-varying magnetic field must be created in some way. The selected method uses a handheld drill to rotate an NdFeB permanent magnet secured to the drill shaft with zip ties. Using an electrical drill serves no practical purposes, since the end goal is to generate an electric current anyways. However, for demonstration purposes, the rotation of the magnet can be thought of as any method of mechanical input. The demonstration setup orients the permanent magnet vertically, and the rotation takes place next to a 400-turn coil of magnet wire around a steel bolt, which has a higher permeability than air. The resulting current in the wire will be alternating in a sinusoidal waveform, so a full wave rectifier circuit is applied. Since the resulting current is still a waveform, a capacitor is included to dampen the fluctuations. The circuit is then routed to a small light bulb, and an Arduino is used as a digital multimeter to measure and display the resulting voltage. Here is the demonstration. I'm glad I finally found a use for these textbooks. The voltage in the circuit reached approximately 2 volts. By Ohm's law, the current can be calculated by knowing the resistance in the circuit. The power is then found, which shows how ineffective this would be as a real generator. A 3D finite element analysis was performed using ANSYS Maxwell to compare these physical results to. Here is the magnetic field produced by the spinning bar magnet. The resulting field impacts the nearby coil. Here is the magnetic field through the steel bolt. The directions of the arrows are clearly reversing as the magnet rotates. And here is the induced current in the coil. The alternating direction of the arrows indicates the generated alternating current in the wire. Here we can see the varying flux linkage through the coil over time. Per Faraday's law, the induced voltage is proportional to the change in this flux linkage. The induced current is inversely proportional to this induced voltage. There are many ways we could optimize this system. We can increase the number of turns in the coil, increase the surface area linked by the coil, spin the magnet faster, select a material with a higher preference of conducting magnetic flux, reduce the air gap, or use a stronger magnet.